Welcome to everybody. This is the first numerical analysis AJS seminar. I will remind you that the seminar will be recorded. Today's speaker is Moaad Khamlich, and the title of this seminar is Model Reduction for Bifurcating Phenomena in Fluid Structure Interaction Problems.
Hi everyone, I'm going to share the screen. Can you see the presentation? Okay, so thank you for joining, and today's presentation will be about my master thesis project, which has been carried out within the MATLAB group at CISA, and it concerned the application of reduced order models for the analysis of bifurcation phenomena in the context of nonlinear partial differential equation. And in particular, we dealt with a particular test case of a fluid structure interaction problem, and which is governed by the Coanda effect, which I will shortly discuss. Before starting, here is a brief outline of today's presentation. In particular, I will begin by introducing, let's say, the theory of bifurcation theory and the Coanda effect. Following, I will introduce some of the necessary elements to understand the algorithm that I've used for the bifurcation analysis. This algorithm has been used to tackle the particular test case at hand, but it is way more general and can be used to approach any other kind of bifurcating analysis for a generic nonlinear partial differential equation. Following, I will specialize the treatment to the system of equation that we solved, which are the one for fluid structure interaction problem. And in the end, I will present the numerical results and a brief comparison of the different test case lists that we have addressed. So, bifurcation theory deals with the study of the qualitative changes in the structure of a family of vector fields. And for our particular case, this family is represented by the solution of a parameterized partial differential equation. And these changes from a dynamical system point of view can be linked to the change in the either the number or the nature of the equilibrium points. And by nature, I basically mean the stability properties of the solutions. And the two images that I've decided to show are some very relevant application of bifurcation theory. In fact, in the context of ordinary differential equations, so ODE, one can provide some examples of cases for which a sequence of an infinite sequence of bifurcation leads the system in a so-called state of deterministic chaos, whereas the study of the onset of the instabilities which are linked to bifurcation is fundamental for defining the operating regimes of engineering system or physical systems. I will just show some brief examples, but for basically just in order to simplify, one can state that every time that there is a drastic change in the structure of the solution for a slight change in the value of the parameters, one may be dealing with a bifurcation. And for those of you who come from the aerodynamical sector, as myself, probably one simple example that comes to mind is the aerodynamic stall. And in that case, the bifurcation is led by the change of a parameter, which is the wind incidence, so the angle between the wind and the airfoil. Another classical example that I'm sure everyone knows is the beam under compression, for which we know there is a critical value of the load, over which the beam is no longer able to maintain a straight shape. And also nowadays there's also a lot of approaches in order to retrieve some physical explanation of phenomena by using bifurcation theory. That's the case in the biomathematical field, for which recently some models have been proposed that try to explain the generation of nerve impulses by starting with a bifurcation theory kind of approach. So the bifurcation we have addressed concern the so-called Coanda effect, which manifests in a lot of different ways, but for our test case, it's enough to state that it can happen when a fluid is exiting from an orifice and attaches to one of the nearby walls. And this effect is amplified in a two-dimensional settings. And that's why we've decided to tackle the case of a planar contraction expansion channel. And this has been done for two main reasons. One is that this is basically a benchmark in the field for studying the instability due to the Coanda effect. So there's a lot of works who has been carried out. However, these works dealt just with the pure fluid dynamic approach, let's say. So there wasn't a modeling of what happens at the interface with the structure. And moreover, another reason is that this geometry can be considered as a extremely simplified setting for studying an earth disease known as mitral valve regurgitation, which basically happens when, due to the defective closure of the mitral valve, the blood flows abnormally from the left ventricle to the left atrium. And in some special condition, under some special condition, it also exhibits this wall hugging behavior, which is the one represented by the simulation on the right. And just to clarify, this is not a time-dependent simulation. Basically, here we are dealing with the steady solution of the incompressible Navier-Stokes equation, and what we are actually changing is the kinematic viscosity. So each snapshot is a steady solution obtained for a different value of the kinematic viscosity, which is the bifurcation parameter in this particular context. And actually, if since the geometry is fixed, this bifurcation parameter from a dimensional point of view is nothing but the Reynolds numbers. So just a brief mathematical description. Basically, we are dealing with the strong formulation for partial differential equation. And just for the sake of simplicity, let's say, we assume that the trivial null solution solves the problem for all the values of the parameter under consideration. This is just an hypothesis, which is obviously not true in our case, because in this case, the reference configuration is the symmetrical solution, so a symmetric jet fluid. But by taking into account these hypotheses, basically we are stating that the bifurcation branches off from the trivial solution. And we can therefore define a bifurcation point as a point in the parameter space for which there is a sequence of non-trivial solution which converges in a proper sense to the null solution associated with the same point. So, from a practical point of view, to effectively study a bifurcating phenomena, we draw the so-called bifurcation diagram, which is simply the trend of a scalar output for different values of the parameter under consideration. And obviously one needs to choose a relevant scalar in order to have a sort of bifurcation pattern. And one example, which is typical for these settings, is the pitchfork bifurcation, which is this pattern of bifurcation. And in its simplest form can be obtained by analyzing an ODE with a cubic nonlinearity. And the thing is that the sign of the nonlinear term give rise to two different sub-patterns, let's say, subcritical and supercritical. And for instance, just let's analyze the subcritical case, which leads to a so-called catastrophe. So basically, it's also dangerous from a design point of view, because let's imagining having the system which it is under the bifurcation parameter, so below the bifurcation parameter, which in this case is 0. Then we will have a stable solution, which is the null solution, and two unstable solutions. If we increase progressively the value of the parameter, we will reach this point, and over it, the stable solution will transition and will become unstable, and there are no other solution. Therefore, in this particular case, by increasing the values of the parameter, the system will diverge indefinitely because there is no other stable solution. A safer setting is the subcritical case, because we will always have a stable solution. So, as I said, our goal is to generate a sequence of solution which belong to the same bifurcation branch. And by bifurcation branch, I'm meaning just solution which shares the same qualitative features. And therefore, the bifurcation diagram will be nothing but the union of different bifurcation branch. and the union all of the bifurcation branch will give us the solution manifold, which basically is the solution to the PDE for all the values of the parameter. But we want to being able to following a prescribed branch. So we want to change the value of the parameter without changing the feature, the structure of the solution. And the algorithm that we used needs a high computational cost model, which is also called full order model, abbreviated FOM, sorry. A reduced order one, which will be abbreviated ROM. And also, the thing is that in this particular case, the rise of the bifurcation is strongly linked to the nonlinearity of the partial differential equation. And therefore, we will also need a sort of nonlinear solver, which in our case will be the Newton solver, and also discretization strategy, the continuation method, which basically is needed because since the convergence of the Newton method depends on the initial guess, we want to actually being able to change the value of the parameter and converging to a prescribed branch. So being independent on the convergence of the Newton solver. So this is the problem under consideration. As I've shown before, it's nothing but a partial differential equation, which needs to be solved for different values of the parameter, and this is the key statement, because one usually solves this kind of problem by a sort of classical discretization strategy. So a classical numerical approach could be using finite elements, spectral elements, finite volumes, or finite differences. And the thing about all those discretizations are that they usually scale proportionally to the number of the degrees of freedom. In the case of finite elements, this is strongly linked to the dimensionality of the space on which we are projecting the equation. And this is an issue whenever one needs to solve a lot of instances of the same problem. And so the question is, if I need to compute a lot of solution to the same problem and just change the values of the parameter, do I need to restart every time from scratch? And the answer is no. If one put in place a sort of reduced order modeling strategy, which is the one that we've used, which actually relies on using an underlying high computational discretization strategy. So in our case, we've used as a FOM model both the finite elements and the finite volumes. But I will just discuss the result with the finite elements because the finite volume approaches was just used in order to carry out, let's say, a comparison between the two discretization strategies. So let's think about disposing of a set of high fidelity solutions relies in first building a vector space by taking the span of the solution that we have, and then finding the subspace of this vector space that minimizes the quantity in the blue box, and which basically is nothing but a sort of average reconstruction projection error over all the data set. And this procedure is called proper orthogonal decomposition. And the nice thing about it is that it can be carried out quite effectively and efficiently by resorting to an eigenvalue problem. And once this optimization problem has been solved, basically you have a set of reduced basis functions which was cardinality is way smaller than the number of degrees of freedom of the full order model you started with, and therefore this basis can be used to perform again a Galerkin projection, and because of the finite dimensional nature of the subspace you are dealing with, you will have a system, an algebraic system of equations. And obviously, since you are starting with a nonlinear partial differential equation, you will end up with a nonlinear system. And that's why the Newton method will be needed at this stage in order to solve the problem for a new instance of the parameter value. So those are the two algorithms that we've used for the reconstruction of the bifurcation branches, both for the FOM model and for the ROM model. And as I anticipated, the nonlinearity of the system and the non-uniqueness of the solution makes the convergence of the Newton method depending on the initial guess. And to actually obtain a set of solutions which are associated with a single branch, a continuation strategy is implemented, which in its simplest form just consists in taking the previous value of the solution, so the one coming from the previous value of the parameter, as initial guess for solving the current instance of the problem. And this was enough in order to follow our branches, but may not be enough for a generic problem. So there's also more complex continuation strategies. So now I will briefly describe the fluid structure interaction problem. And the equation, so the system of equation we are solving is nothing but the Navier-Stokes system for the fluid and the momentum balance for the solid. And there is also room for choice concerning the constitutive relation for the solid phase. And actually, we've dealt with two different cases, an elastic model and a linear elastic model and a non-linear hyperelastic one. And in this particular problem, as I said before, but I will recall it, the kinematic viscosity will be the bifurcation parameter under investigation. And the main problem when dealing with a fluid structure interaction problem is that generally the equation of the Navier-Stokes equation are solved in a Eulerian framework, so in a special reference system, and therefore the mesh is fixed. However, when we are dealing with a fluid structure interaction problem, the mesh needs to be in motion because the fluid resolution domain needs to be consistent with the solid deformation. And this is solved in various ways, but the one we've chosen is to use the arbitrary Lagrangian Eulerian formulation, which basically just consists in doing the pullback of the Navier-Stokes system on a reference and fixed configuration. And this is done by solving a problem and introducing a fictitious displacement of the fluid resolution mesh. So the best strategy to do that is basically stating that the deformation of the mesh needs to satisfy a Dirichlet boundary condition on the interface. And this is obvious because the mesh displacement of the solids needs to be equal to the mesh displacement of the fluid at the solid fluid interface. Afterwards, since we need to do the pullback inside the fluid domain, one needs to extend this fictitious displacement inside the fluid domain. And this is done in, there's a lot of choices also concerning this, but what we've done was to extend it in an harmonic fashion. So basically we are setting up a Poisson problem, and therefore there's like a spread in a heat equation fashion of the solid displacement inside the fluid domain. And once the problem is solved, the last thing to do is to pull back the Navier-Stokes system on this fixed reference mesh. And yeah, the system then obviously needs to be completed by coupling condition between the two phases. And in this case, we will have the Dirichlet boundary condition I was speaking about at the interface, but also the equality between the velocities and the equality between the stresses at the fluid structure interface. And then the last thing will be to introduce also a sort of a set of boundary conditions. The one we've chosen was to actually impose a gradient of stresses between the inlet and the outlet of the channel in order to animate the flow. Then we will obviously have a sort of non-slip boundary condition on the other boundary of the solid on the fluid resolution domain. So concerning the numerical results of our study, the first case we have addressed was the rigid structure case, so the one we've shown when I was speaking about the Coanda effect. And basically here we are solving just the Navier-Stokes system in absence of a solid phase. And the bifurcation diagram which we obtain is shows a the typical pattern that I've shown. So it's a pitchfork bifurcation, and it's a supercritical pitchfork bifurcation. Therefore, basically, above the bifurcation point, which we have estimated to be 1.9 for our particular setting, there is just the single stable solution, a single stable solution, which is the one of symmetrical jet. However, below the bifurcation point, we have also the coexistence of three different solutions. So the symmetric one keep existing but changes nature, so it becomes unstable. Whereas we have two new solutions, which are the one which exhibit a wall-hugging jet. And the important thing is that the algorithm we've used to follow each of these branches is the same. The only difference is about the the direction of exploration of the parametric interval. So the second test case concerns the fluid structure interaction problem. And in this first setting, we are dealing with a linear elastic solid. And basically, if we look at what happens at the fluid phase, and we draw again the bifurcation diagram, and sorry, I didn't state it, but in order to obtain this kind of diagram, we took as a relevant scalar output the vertical velocity at a point in the axis, which will obviously be a valid indicator because in the case of symmetric jet, this vertical velocity will be 0, whereas if we have a wall-hugging jet, it will not be 0. So yeah, when we are looking at what happens at the fluid, it will be more or less the same of what we've seen before, but we were interested in understanding how the bifurcation manifests at the solid phase level. And in order to do so, we plotted the maximum of the amplitude of the displacement fields for the upper and the lower leaflets. And as we can see, so it's this plot, above the bifurcation point, these two feeds exhibit the same trend. So both of the leaflets they forms symmetrically, whereas below they diverge, and this happens because once the bifurcation has occurred, we have also an asymmetrical velocity and pressure fields, which will obviously result in an imbalance of the forces which acts on the structure interface, and therefore we have an asymmetry on the displacement, on the solid displacement fields. And the last thing we did here was to we were interested in obtaining a sort of bifurcation diagram also for the solid phase. And in order to do so, as a scalar output, we have just used the difference between the maximum deformation in absolute value of the upper and lower leaflets. So from a ROM model point of view, in order to recreate the previous FSI problem, we conducted a proper orthogonal decomposition on each of the unknown fields, and the average reconstruction error as a function of the number of bases is the one on the left. And since this is a logarithmic plot, we can observe an exponential decay. And in particular, we have found that a single mode was sufficient to retain more than 99% of the variance of the snapshot for both the displacement fields. So for the fluid displacement and the solid displacement. And this can be justified in light of the fact that we are solving a linear elastic problem and for the solid displacement, whereas for the fluid displacement, we are setting up an harmonic extension, which is also linear. And therefore, since these problems are less complex than the counterpart represented by the Navier-Stokes equation, we expect these fields to be reconstructed more effectively. And the plot on the right refers to the trend of the relative reconstruction error as a function of the kinematic viscosity when we are using 16 bases, and this error is acceptable, and we've got like the highest one is the one for the pressure, and it's more or less equal to 9 to the minus 3, and all these error show an oscillatory trend. And actually, if one counts the peaks, he will find that there are 16 exactly, and that happens because each basis helps the convergence in a particular sub-interval of the parameter space. So finally, we dealt with the nonlinear model for the solid phase, and we've chosen to address to use an hyperelastic nonlinear model known as some Venant-Kirchoff. And in order to carry out a comparison with the linear counterpart, obviously we have taken the same values for the constitutive relation. And what we have seen is that even though the deformation for the SVK models are greater than the ones of the linear one, and this can be seen in this plot. I'm sorry because the labels are really small, but basically this is the behavior for the SVK model for the upper and the lower leaflet, and these are the ones for the linear one. However, the linear model respond in an amplified manner to the bifurcation. So here we've got the bifurcation diagram for the solid phase for the linear model, whereas the red one is the same diagram but for the SVK model. And the last comparison we carried out was between all the models under consideration. So we've got the rigid structure case, which was the first one we have shown, and then we have two linear models, which basically changes. One is more stiff and the other is less stiff, and then we have the nonlinear Venant-Kirchoff model. And what we have observed is that the increase in structural stiffness in the linear case leads to a delay in the bifurcation, while the Venant-Kirchoff model delays still the bifurcation with respect to the rigid structure case, but it anticipated with respect to the linear counterpart. So, as a conclusion, the main contribution of this work was to study for, let's say, the first time, or at least for this is our knowledge, the bifurcation due to the Coanda effect, but in a multi-physics context. And this was done in order to understand the effect that the structure may have on the bifurcation. And moreover, we were able to use the reduced basis method in a, let's say, very complex and stretched setting. Actually, we are dealing with a nonlinear system with 6 unknown fields that undergoes a bifurcation in the parameter range under consideration. So we were not, let's say, sure that the bifurcation method, the reduced basis method will perform effectively, but we were proven wrong. So that's nice. And the next steps will surely be to develop an eigenvalue analysis on the partial differential equation, and this will be done in order to have a quantitative indicator for the bifurcation points. Basically, if we perform an eigenvalue analysis, we will be able to exactly analyze the scale of the delay, which is something that at the moment has been done just visually by inspecting the plots. And moreover, one thing which is which can be done is investigate some sort of control on the stability properties of the solution in order to drive the bifurcation, and this can be done through some optimal control approach. And the last thing, which is a state of the art for reduced order modeling right now, is to integrate our framework with machine learning frameworks, for instance, by using a neural network coupled with the proper orthogonal decomposition, or by using physically informed neural network. And yeah, so this is the bibliography for the work. In particular, if you are interested, the last item is a preprint which investigate more in depth what I've spoken about, and all the numerical resolution has been carried out with the open source software. In particular, we have used Urbanics for what concerns the model reduction, which is an interface built upon the Phoenix project, and Multiphoenix, which helps the definition of multi-physics problems, and it's also an interface to the Phoenix library. Whereas for what concerns the finite volume case, we've used the Ithaca finite volume library, which is instead built upon OpenFOAM. So thank you for your attention, and if you have any question, I'm glad to answer.
As a warm-up, I have one maybe.
Okay.
Can you go back to the slide with the algorithm?
Yes. No. Oh.
Maybe as a first question, I would ask, how do you choose the initial guess for a parameter?
Like the very initial guess or the current one? Because the initial guess for when the loop is started, as I said, is linked to the continuation strategy. So basically, you are just using the previous value of the solution. Whereas as a very initial guess, we are just using the trivial solution, and this has been working in our test case at least.
As continuation strategy, you mean the previous parameter?
Yeah, you're using as an initial guess for the current instance the solution of the previous parameter value.
For example, you don't need to add additional intermediate steps from the optimization process.
No. Yeah, and the thing is that also maybe that's something I didn't explore, but the convergence, even though I've said that we were able to obtain all the branches, for instance, these two wall hanging branches can't be obtained simultaneously because they are just symmetricals. So if we, for instance, the convergence, let's say, of the solver will depend on the discretization, so on the underlying mesh. But if you really want, let's say, to obtain the other branch starting from the solution of one thing that you can do is just reflecting the field and using that as an initial guess in order to obtain the other branch.
Are there any questions?
Yeah, if I may. As scalar output, you choose the vertical velocity at a given point.
Yeah.
How does the choice affect all the methods?
No, basically, let's say that the scalar output is just used in order to obtain the bifurcation diagram. So it's let's say, visual representation tool for what concerns the analysis, so the investigation. But actually, you can choose any other relevant scalar output. And if you make your choice in an effective way, then you will find always a pitchfork pattern, but this doesn't influence the underlying method.
Are there any questions also from online audience? I don't know if they otherwise, I have still one.
Okay.
If you come back again to the algorithms.
Okay.
Okay. May I ask, is your Jacobian symmetric positive definite? No, right? I mean, it's a bit. There is an interaction term, so you should not.
No, it's not.
I'm trying to use another method rather than Galerkin projection. Because, for example, Galerkin should be more efficient in this case when there is a bit of reflection, when Jacobian is not symmetric.
Actually, we have not used any other method. So we've just investigated the Galerkin projection because let's say that this same framework has been used to tackle a lot of different bifurcating problems. So my supervisor, which is Federico Picchi, has been using this same machinery for quantum mechanics and other kinds of instabilities. And therefore, I just, let's say, applied an existent framework to the particular test case. But that can be a suggestion for future investigation.
Any questions again? Well, let's thank again, Mark. See you at the next AJS.
Thank you all. Bye-bye.